Okay, so what we're going to do first here is, just like it says on the screen, we're going to predict the effects of filters on source signals. Easy enough, right? Hopefully. So here we go. All right, so why do we need to know about filters? Like, what is the whole deal? How are we? You're in a class that's supposed to be about voice production, but we're talking about filters, which are things that we use in audio production a lot. Why are we talking about filters? Well, if you think about the source filter model, we call it the source filter model for a reason, and we're using these terms that are audio production terms: the sound source, the filter, and the output, the input and the output, all this kind of stuff. This is all, audio production or kind of engineer electrical terms. Well, it's all really analogous to the same thing, right? Our power source, of course, is is breathing, so the air that we're taking into the lungs. That's our power source. We have our sound source here at the larynx, which of course we've talked about. But then we have to filter the sound coming from the larynx to turn it into something that we can actually hear. These words that you're hearing right now, the words that are coming out of my mouth, are filtered from just this laryngeal buzz. Anything aside from pitch change is something that's being filtered here that you can hear. And of course, that's not like 100% true. There's some timbric changes that you like vowel quality. We've talked about some jitter and shimmer, and if you've taken 310 with me or anybody else, you know that there are other things that can happen with phonation that aren't just frequency change. But I mean, like, let's just go broad view here: frequency change, and then changing the other aspects of the sound. Very broad. Most of the variance is going to be sucked up by these things. So just know, of course, further on in your classes, depending on what trajectory you go, you might figure out that there are other little pieces that come in to explain some of these things. But broad picture for this class: frequency change, and then filtering the sound into these sounds that you're hearing. So we can also use this knowledge about filters to decompose signals. So we can take a speech signal, this here, the output sound, and we can decompose that. We can figure out what created that. So we can work backwards, right? So if we take this output sound over here, which of course I should have my laser pointer on. There we go. So we take this sound here, we analyze it with something like Prot or Audacity, Wavesurfer, any of these. And so then we are going to work backwards through that. What we want to do is we want to see that there is some sort of filter that looks like it's applied here. We get these peaks like this. Of course, the laryngeal source isn't doing that. So then we can interpret what the filter must look like. And then we can interpret what the laryngeal source looks like. We interpret the filter looking like this, or however it looks, then we can also get an idea of the shape of the filter. So just by measuring output, this, like if you took the sound from this video, you could measure the output and you could guess by the shape of the envelope what vowel phoneme or some consonants that I'm actually voicing at that moment, just from the envelope. I mean, you could listen to it and probably guess that way too, but let's say that the audio on your computer was broken. You would be able to look at this and say, based on the shape of this envelope or filter, resonant frequencies that we see, he's saying an ooh phoneme right now. All right. And then it also, filters in general can also filter noise and unwanted components. This is somewhat important in speech, but also kind of an audio production thing. So if you're recording speech, you can put it through a filter and knock out frequencies that aren't important. Okay, so filters, just like resonant cavities, what we've been talking about in the last module, they're going to amplify or pass They're going to amplify the frequencies that they correspond to, or they're going to allow them to pass. It depends on if it's just a band pass filter or something that's amplifying. You can do either one. So it's either going to accentuate or just allow the frequency to pass. The things that it's going to allow to pass are the frequencies that correspond to the resonant frequencies of that cavity, of that filter, whatever we're talking about. But essentially, we can think about it like this. A resonant cavity creates a filter. So we don't really need to think of them as separate things. They're all kind of synonyms for the same term. So we have resonant cavities, which are going to create these resonant frequencies, these resonance peaks. Those resonance peaks are a filter. And then, of course, filters also attenuate frequency components of input signals. Of course, that should say input signals. Oh, Patton. So filters are going to attenuate frequency components of input signals that do not match their resonant frequencies. So if they're allowing things to pass that do match the resonant frequencies, they are going to stop frequencies that don't match the resonant frequency. So let's take a look at this like cartoon demonstration that I've made here. So what you've got on the left, this is a frequency component of a signal, right? This is just the typical thing that we've always seen. We've got this up here, frequency component. I didn't add the slope to it. It's fine. You can think about this as like 100, 200, 300, 400, 500, 600, 700, and 800 hertz, but they're kind of just, any frequency you want it to be. And then this is a filter. Right here, this is going to be a band pass filter right here. And then, of course, over here, this is attenuating everything that's coming through. So this isn't going to amplify anything. It's just going to allow the frequencies to pass. But again, like I said, some filters can amplify, some can just pass. The resonant cavities typically amplify a little. But like in Prot and Audacity, you can amplify a lot. Okay, so let's see what these do. We're going to turn them. I'm turning them just so you can kind of watch them dock together like two spaceships, or like a spaceship and a space station, right? So we're just turning them slightly to the side. The orientation doesn't really matter. It's the same kind of graph. So what's going to happen here is these frequency components are going to come through the filter like this, right? And so you can see they're moving through the filter. I had to put it slightly offset so you could see the ones that are actually coming through, but it's okay. So if we jump back, all of this sound with all these frequency components are traveling through the air or through the throat, and they come to the filter, and then it kind of acts like a cheese grater sort of thing, and like this is a hole in the cheese grater and this is metal, and so parts of the cheese come through and other parts of the cheese do not come through, right? So those parts don't come through. They're not accentuated. They're not allowed to pass. They're attenuated. And those are allowed to pass. And what you end up with is this. What comes out is, if we did say that this was 100, 200, 300, 400, blah, 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 we've gotten rid of 1, 2, 3. So you end up with 400, 500, 600, and 700. 800 was also not allowed to pass. So this 4, 5, 6, and 700 hertz frequency, this is the piece of cheese that's been allowed to go through the cheese grater. And that's how a filter works. Yeah, and then we can turn it back up and see it the normal way that we tend to think of it. Okay, so let's use that knowledge that we've got to take a look at what's going to happen to this signal when it goes through this frequency representation of the filter, right? So it's going to go through this filter. This input signal here is going to go through this filter here. What are we gonna see? What's going to come out? Go ahead, pause the video if you want to take a look at it and think about it, because I'm just gonna show you and we're going to talk about it. So, all right. We end up with this. And one way that you can see that is if you look here, the center frequency, we're just going to look at this curve first, and then we'll move to the next one. The center frequency here is 500 hertz. And we see that we've got 500 hertz here. So this is going to pass completely. That's why over here, 500 hertz is just as tall as it was over on the left. 500 hertz passes completely. But you can also see that it doesn't just cut all the way down immediately like my filter did. Mine was like a square. Like that. So frequencies either completely passed or they were gone entirely. Well, this, they're not gone entirely. They're just kind of like a gradual slope drop off to it. This is much more like what the vocal tract does to sound. There's not a steep drop off like the filter I showed. It's more of this kind of gradual sine wave kind of resonant frequency filter that it puts on things. So you get this kind of nice undulating pattern. Anyway, so you can see that it doesn't cut off immediately. You can also, if you look at the center frequency here, which is 500, the center frequency here is 1500. And so halfway between those is going to be 1000. And that's where the sound is going to pass the least. Notice that it doesn't hit the 0 mark. The 0 mark is down here. So we will expect that none of our sound will be attenuated completely. And that's actually what we see here. None of our sound is attenuated completely. And this should be 1000. So if we go 500, 625, 750, we'll have another one in the middle, which should be, what, 875. And then 1000 right here. And that's our lowest peak. So we just kind of match these up. And that's the one. Okay, let's do another one. Our input signal's on the left. It's going to go through this filter in the middle here, or on the right. There's going to be another picture on the right in a second, so it'll be the middle. What's going to come out of this? Go ahead and pause it right now if you want to take a look at it. You should. You should pause it and try to answer it. And I'm just going to go on and answer it. So what you see is some of these frequencies pass completely. Then there's a very steep drop off to this filter, which cuts 625 in half. And then everything else is gone. And how do we know that? Well, we've got 550, looks like it's about here where this filter starts to drop off. Then we've got 750 where the filter is completely dropped off. And so if we look over here, we've got 500, so 550 somewhere in the middle here is where the filter starts to drop off. 750 is where it's 0. 625 is in the middle. So it should be cut roughly in half. And everything to the left of that is going to pass. Everything to the right of 625 is going to be gone. And so then we just transfer that information over here. Pass, pass, pass. Halfway. And everything else is gone. Next. This is similar, but now instead of having everything pass and then a steep drop off, we've got kind of a steep onset, and then some things pass, and then we have a steep drop off. So it should look kind of like the other one. Go ahead and pause if you want to take a look. And here's what we got. 125 is now completely cut out. It was there in the previous one. It's gone. Why is it gone? Because you can see that 250 is where this filter reaches peak. 150 is where it's at 0. And this harmonic of 125, of course, is to the left of 150. So it's not going to pass at all. So you have these three passing completely. 625 is still cut in half for the same reason it was last time. And then nothing else. All right. Now it's a little narrower. Still got some steep onsets and offsets. But it's a little narrower. So we would expect less to pass through, right? So go ahead and pause. And here's the answer. Hey, absolutely nothing passes. But why? Well, look. So we've got 250. This filter is at 0. Nothing is passing at 250. And then it's allowing things to pass completely from 275 to 325 back to 0 at 350. Well, shoot. Look over here. The frequencies that we have start at 250. Then there's not another frequency in the signal until 375. So 250 to 375, 250 to 350, we're only allowing things to pass that are like right here. And there's nothing in between those signals. So nothing passes. So you have to look at the frequencies at the bottom of the filter. You have to match them up to the frequencies that you see in the input signal, and then you can figure out the output signal. I think I have one more. I think this is the last one. So let's take a look at this one. Go ahead and pause. And here's the answer. Only 100 hertz passes. This is kind of similar to the last one. It's been shifted to the left a little bit. And the reason why just 100 hertz passes is because you've got 50 to 150. 100 hertz is roughly here in the middle. And between 50 and 150, we've only got one frequency over here, which is 100. And so that one's going to pass completely. Everything else, everything to the right, is just knocked out because it's not allowed to pass by this filter. I think that's the last one. Oh, no, I have another one. Whoops. Oh, I showed you the answer. Sorry about that. Okay, well, if you didn't see that, here's another one. This has moved a little bit to the right. I think it's a little bit wider. No, it's still 100 hertz wide, so it's just moved to the right a little bit. What do you think is going to pass now? 300 hertz passes now instead of 100 in the previous one. Why? Because if you look at the filter, you've got 250 to 350, and 100% is going to pass between 275 and 325. Well, what's between 275 and 325? 300, and nothing else. Nothing else is even between the zero marks on those, so everything else is knocked out. 300 hertz is allowed to pass. All right. Well, to sum up what we've looked here, this is how we're estimating the effect of filters on source signals. If you want to put it in terms of the larynx and actual speech, what we're looking at is how the shape of the vocal tract might shape the laryngeal buzz. Yeah, it's like an easy cartoony example, but you know, later in this module and next module, we're going to be looking at the actual vocal tract and how it actually modulates the laryngeal buzz. This is just kind of preparing us for that, but same basic idea. This is how the vocal tract is going to shape the sound from the larynx, from the laryngeal source. And then also, it's how we design filters to extract specific components of a sound source. You can think about this in two ways. You can think about it like we want to produce a sound, and so we can shape our filter, our articulators, to produce that sound, our vocal tract. And then also, if we're doing some sort of audio editing, if we want to produce a tone or something like that, we can create a filter to produce that tone. Two completely separate ways of doing it, but it's basically the same thing. So if I want to say E, I can conform all of this to create the right filter. If I have a thing of like a buzzing sound in Prot or Audacity, I can create a filter that has very similar properties to what I would use here to say E, to then turn that buzzing sound in Prot into an E, or something that sounds like an E. So we kind of work backwards to see how a resonant output can become a non-resonant signal. We can see what the filter looks like, and we can design filters that way. All right, that is the end of this submodule, so see you in the next one.